Hey everyone. So one of the things that I remember hearing at the turn of the new millennium was that China was in a boom. They had loosened up their economy. They were trying to encourage people to get off the land and into cities. And so I haven't actually confirmed this statement, but my understanding is that there are more than 100 cities with more than 1 million people in China. That's a lot of cities with more than a million. Um, wow, that's a lot of cities. So let's take one of those cities, Shenzhen, in 1990. It had a population of 1,081,620 people. In 2000, 10 years later, 6,480,340. I'm sorry, the population grew by 5 million in 10 years. Tucson is just barely at a million now. Can you imagine adding 5 million in only 10 years? Okay, that's exciting growth, except that by 2010, 10,358,380 million people. OMG, it's a, that's a growing town they got there. Um, yeah. Now, some people will wonder about the accuracy of these numbers. The government in China is not always particularly honest with the numbers that it posts. Um, so we'll take this with a grain of salt, but let's build a model now and see just sort of, if A, we can build a model, and B, let's use it to predict what the population would be in 2020, and then we'll Google the population of Shenzhen in 2020 and see how our model fits. Okay, so now, yeah, what are you going to do here? Because here you've got three pieces of information. And so I'm kind of interested, what, what method will you use here? And here's why I ask. If this is an exponential growth curve, and going up by 5 million in 10 years feels like exponential growth to me, but then from 2000 to 2010, we went up about 4 million, which, don't get me wrong, is still 4 Tucsons were added onto the city. But this amount is actually less than that. So you've got a choice to make here. And that is, do I build the model with the first 2 data points? Do I build the model with the second 2 data points? Or do I build the model with the first data point and the last data point? Because what I know is all of these models are going to be different. I mean, we know this because here we went up by 5.5 million, but here we only went up by 4 million. Yeah. So one of the reasons that people with math degrees get a lot of money for doing math for companies and organizations around the planet is because A, they know that we're going to get 3 different models here depending on which ordered pairs we use, and B, they can maybe help us figure out which one is better model for us to be using. I'm just going to use this point and this point. Yeah, because I don't have a lot of information. I don't really know what's been going on in Shenzhen the last 20 years, except the population has been growing. And so I want to talk about over that whole 20-year period. Okay. So the next thing I want to say is that, again, we could use these ordered pairs. Oops, 1, 0, 8, 1, 6, 2, 0, and 20, 10, 10, oops, 3, 5, 8, 3, 8, 0. I can use these ordered pairs, but again, this is going to then build the model back to time equals 0 is the birth of Christ. And yeah, I don't want to do that. I would prefer instead to say that t equals 0 is 1990. So this is going to be 0. And 2010 is 20 years later, so I'm going to have a 20 here. I want to do that because that's t equals 0, so that's the initial population. Okay, so if I'm using p equals p sub o e to the rt, I know that this number is p sub o. I don't have to use two equations with two unknowns to figure this out. I can just know because if I plug in a 0 here, 0 times r is 0, e to the 0 is 1, 1 times p sub o is p sub o, and so p sub o must equal that output because I plugged in a 0 on this side. Nice. All right, so let's start building this model. I'm going to have p equals 100811620 e to the rt. Now, I have the second ordered pair that I want to plug in. Time, not 2010, but 20 years after 1990. So I'm going to plug a 20 in here. And this is the number of people that I've got 20 years later. So I'm going to put that over here. 358380 equals 1081620. Yes. E to the r times 20. Okay, so can you please finish solving this? I know, we're going to look for r now. That's what we need to do first. Yeah, I'm doing it too. But I don't want to give it away. I want you to be thinking about it. Because really, this is day 3. You should be able to do this. Maybe not the setup, looking at 3 ordered pairs. But from this point on, for sure, you need to be able to solve this. So I divide both sides by my initial amount. I take the ln of both sides, and then I divide by 20. And I get that r equals 0.11296679668. That means that the population is growing approximately 11.3% per year. Now, when we did the Tucson problem in the last video, our population growth was closer to 3%. Much faster growth. Yeah, hugely fast growth. So I'm going to take this rate and I'm going to plug this rate in here. 0.11296679668t. So here's my population model. There's the original amount. I used a second ordered pair to help me find the rate. Nice. And what did we want to know? We wanted to know the population in 2020. And if this was 20, then 2020 would be when t equals 30. So let's plug that 30 in there and see what we get. So I take my r value and multiply it by 30 and use e raised to that power, and then multiply all that times this initial amount, 1081620. I get 32055341222. So, according to our model, there should be 32 million people in Shenzhen today, if that rate of growth continued. All right, well, I'm going to go over to the Google now, And I'm going to say, hey, what's the population in 2020 of Shenzhen? Shenzhen's 2020 population is now estimated to be 12,356,820 people. That's very different. Look, it went up by 5.5, it went up by 4, and now it's gone up by 2. So it's growing, but growing at a decreasing rate. Growing at a decreasing rate. So instead of this kind of growth, which is what we maybe were experiencing, I think we're looking at growing at a decreasing rate, almost as though we were headed to some sort of maximum asymptote. And that's often why a logistic model is a better model than just an exponential one. An exponential one is great for this part, finding out when we keep increasing faster and faster, but most population models actually top out. Yeah, when I was a kid, living in New York City, we talked about having, about 7 million people there. And, you know, the population has been growing, but it's only about 8 million now, 50 years later. So, yeah, I want to say that logistic model, a little better. Sadly, we're not going to dig much into logistic models here. We're just going to be sort of a little more casual and use our PERT models. Um, wow. Oh, in 1950, the population of Shenzhen. I mean, can you say village? And then what is it today? 12,356,820 in 2020, 1950. Things have changed. That town has grown a lot. All right, what's next? Oh, yeah. So, remember in the last video how Arthur Andrew was walking home one day and thought he found an elephant tooth in that riverbed? Well, I want to do another percent problem, okay? And so this percent problem deals with um, a piece of art, a Vermeer painting. Vermeer was a Dutch painter, and if you haven't seen his work, I encourage you to Google it. Um, yeah, Tim's Vermeer. I think it's on Netflix. You might want to watch that. But anyway, Vermeer lived 1632 to 1675, and when you realize what he was painting at that point in human history, it's one of those pretty amazing things. So, he painted some paintings. Actually, he painted very few paintings. I think he's only uh, listed as something like 30 or 32 paintings. And so, when one of them came up for auction in in 1983, one of the things that auction houses have to do is that they have to authenticate the works that they're selling, or they could get in big trouble if it turns out that in fact the thing they're selling is a fake. So provenance, where does this come from? How do you come to have it? A paper trail of ownership, but also sometimes actually doing carbon dating on these works of art is something that helps places like Christie's figure out how old an object is. So, um, yeah. So, what was expected was that 95.98% of carbon 14 should remain if Vermeer painted it. And when they tested it, 9.944% of carbon-14 remained. Much more of the carbon was still there. So what I'd like you to do is, given this, and of course remember the half-life for carbon-14, I'm using 5730. Okay? So what I'd like you to find out is, if this percent remained, and this is the half-life for carbon-14, how old is that painting? I know. This is in fact how Interpol knew exactly who to go arrest. Solving this problem. Okay, so let's do it. We know that 99.44% of the carbon-14. Remember, in the last video, we said percent is equal to Q over Q sub O. And so I start off with this equation, Q equals Q sub O e to the KT, and I divide both sides by Q sub O. These go. And so e to the KT is Q over Q sub O, and since Q over Q sub O is percent, I know percent is just going to be e to the KT. All right. This. How do I use half-life? Remember, we have a shortcut to find K. What's our K shortcut? What's our rate shortcut in half-life problems? ln of half over 5730. It's ln of half because we're doing half-life, and on the bottom we put the time to half-life. Okay, so we've got a percent. Let's put that in over here. We've got a K. Let's put that in over here. And let's see what we can do about solving for T. So I'm going to have percent equals e to the KT. The percent is 9944. And our K value, e to the ln of a half over 5730 T. So I need to solve this equation. Well, I see that T up there in that exponent. I need to bring it down. And the only way I can bring it down is in the presence of a log. So now I get ln 0.9944 equals ln of a half over 5730 T, because the ln of E is 1. I'm solving for T, so I want to multiply both sides by 5730, and I want to divide both sides by 1/2. 5730, and then 1/2. I'm going to multiply by 5730 and divide by ln of half. Okay, let's see how old this is. We've got 5730 times ln 0.9944. Don't forget to close those parentheses, divided by ln of I think I've made a mistake, because it's not supposed to be 4 years old. Percent. Take the ln of both sides, bring that down, multiply by 5730. Oh, I did 573. Okay, I'm going to go back to that and add that 0. 46.423 years old. Now, if Vermeer is painting in the 1600s, how can this painting only be 46 years old? If we take 1983 and we subtract this answer, we get 1936.577 years. Yeah, so it turns out that there was this gentleman. His name was Hans von Meergen. Oh, sorry, Meergeren. Um, yeah, he actually got into a bit of trouble in the 1930s in Europe for forging Vermeers. Sadly, though, Interpol went to get him and discovered that he's been dead a while. But the painting is now attributed to him and did not sell at auction as a Vermeer. Mystery solved, Scooby. All right. Um, Next, in uh, the last video, we talked about what happened with the poor people on Bikini Island um, when we decided to do some weapons testing there. And I wanted to tell you about something that you may or may not know about, and that is the neutron bomb. The neutron bomb was developed in the 1950s and 60s, um, and it came up uh, it came up that we needed this kind of weapon, and I'll tell you about it in a moment, because the nuclear weapons we were using at the time had a drawback. So, here's what we were doing. We were using U-235, which has a half-life of 704 million years. Now, let's imagine that you were a country and you really wanted what that other country had. And so you thought, well, maybe I should drop a bomb on them and then go take their stuff. The problem with that thinking is that if you're using this in your bombs, it's gonna be 704 million years until you have only half the original amount. So it's not gonna be safe to go and get those things that you wanted. Yeah. So instead, the neutron bomb was developed, and its tritium has a half-life of 12.32 years. And I will tell you that I remember hearing as a child in the news one of the newscasters saying, we could drop this weapon on the Middle East and then go and take all the oil in our lifetime. It's kind of chilling. And we built the neutron bomb. The neutron bomb was designed to kill off all the organics and leave the stuff. You wanted some apartment buildings? No worries. We'll just kill all the organics and you can have the stuff. We haven't made these in a while. We made some. I don't know if we got rid of them all. You might want to look into that. So here's what I want to do for comparison's sake. Okay? I want to know when only 1% remains with this model and with this model. How long will it take me until only 1% of the original fissile material remains? Okay? So you're going to have to build a U-235 model, you're going to have to build a tritium model, because we have these two different half-lives. You're going to have to remember what we said a few minutes ago about percent, or in the last video about percent, and we want to set percent equal to 1. Okay? All right. So now, believe it or not, this should not take you a long time. Here's how I know that. If I'm using Q equals Q sub O e to the kt, and I remember that Q over Q sub O is percent, then I can say 0.01 equals e to the, what's our shortcut for the k in half-life problems? Ln of a half over time for half-life. So I'm going to have ln of a half over 704 million years. Don't forget the t. And my other model, 0.01 equals e to the ln of a half over what was the time for half-life for the tritium? 12.32 years times t. So I need to solve each of these equations. Okay? But really, if I'm not owning the knowledge, this is probably, there's no way I'm getting here that fast. I'm probably confused and scared and frightened. So please, watch the videos a couple of times so that this knowledge gets in your brain. We need to take the ln of both sides of each equation. That'll allow me to bring down this exponent. And then I'm going to multiply both sides by the reciprocal of this and the reciprocal of this to get t by itself. Okay? Will you try doing that so that we can compare answers and you can know whether or not what you're doing is correct or not? Okay, so for this one, I got t was equal to 46777274758. And by the way, that's a number of years. Hundreds, thousands, millions, billions. 4.6 billion years until we have only 1% left. That's a long time. I don't know that any of us is still going to be around then. But what about this one? I've got ln of 1 divided by 12.32, and then I want to divide by ln of, and I get t equals 81.852 years. The United States had said that it was building nuclear weapons as a defensive tool only after World War II. We would only use them if they were used on us first. This kind of suggests that's true. This suggests maybe we were thinking about using them in a different way. I don't believe there are any neutron bombs currently in active stocks of our nuclear arsenal. I don't know if they've all been decommissioned and taken apart, but you might want to look into that. Okay. So, last problem. I got a graph. I want to write the equation. Here's y equals 0. I've got 2 points, 0, 4, and 2, 1, 4. Will you please write the equation for this? Hey, and before you go off and do that, is this exponential growth or decay? Well, the numbers are getting smaller and smaller, so I'm looking at decay. So when you build your model, check to make sure that it's a decay model. Okay? All right, well, welcome back. I know that even though I prefer using a times b to the x for these problems, that many students either prefer to continue to use PERT, or they're not actually hearing me when I say, I think it's easier to use this one. And so they just keep using the one they've been using. All right, so let's plug in this point. We plug in a 0 here. 0 times r is 0. E to the 0 is 1. 1 times p is p. And our output is 4. So I get p equals 4. Nice. So now I can write a equals 4 e to the rt. And we'll plug in the second point. 1/4 equals 4 e to the r times 2. I need to solve this equation for r. I'm going to divide both sides by 4. And you know, it's the funniest thing, because people do this division by 4 on both sides, and I've seen so many students write the number 1 here. But if I'm going to divide both sides by 4, I should actually have 1 over 16 over there, not 1. Okay? So I'm dividing both sides by 4, and that's going to give me 1 over 16 equals e to the 2r. I need to take the ln of both sides and divide by 2 to get r alone. So I want the ln of 1 divided by 16, and I want to take that number and divide it by 2. So I get that r equals negative 1.386294,361. And so now I feel like I can build my model. My model is going to be y equals 4 e to the negative 1.3862914361 t. Ta-da! There's my model. That's if I'm using PERT. I don't like using PERT for these problems. I like using a times b to the x. Now, if I plug in a 0 for x, b to the 0 is 1. 1 times a is a, and on the other side I have 4. So 4 equals a. But now let's plug in this point for x and y, and this in for a, so we can solve for b. 1/4 equals 4 times b to the second. So when I divide both sides by 4, I'm going to get 1 over 16 equals b squared. And if I take the square root of both sides, I end up with b equals 1/4. So my equation then, remember that a was equal to 4. 4 times 1/4 to the x. No, you can't multiply these together and have it be 1 to the x, because exponents happen before multiplying. Though I could actually, and look how sort of graceful and elegant that is compared to that. You could actually take this problem a little further. Isn't 1/4 the same as 4 to the negative 1? And then when I raise a power to a power, I multiply them. And look here, I'm multiplying and the bases are the same. What can I do with the exponents when I'm multiplying and the bases are the same? What do I do here? Multiplying, the bases are the same, I add the exponents. And so this could end up being 4 to the 1 minus t. That's this. And that's pretty fast and easy. And, ooh, so much less labor intensive. And I didn't need a calculator for this. I definitely needed a calculator for that. Okay, so there's the end of the new material for logs and exponentials. The next videos will be review videos. All right, see you there.